All right. Can everyone still hear me? Can you guys see my screen, hopefully?
Yeah, we can see.
All right. Excellent. All right. So today we're going to start project 3, or final project. It's also the lightest, and sort of recognizing that, mid-November onwards, your to-do list just grows longer. The due dates just come faster and accelerate. So the acknowledging that, I want 367 to be genuinely useful. At the same time, I don't want it to be something that gives you nightmares. So related to that, again, the idea here is if you just show up for the next two and a half or 1.5 weeks of class that's remaining, we basically go through this and do it in class, step by step. You'll do it with me, and you won't have any extra work or outside work to do. That said, we'll talk about the calendar here in a minute, but the name of project 3 is called Urban Cellular Aggregations. Hopefully you guys can see this image, and it's showing up on your screen if you're looking at this. So if I go to, again, I'm in the 367 course shell here. Modules seem to be the best way to sort of organize these things. So, okay, here we go. So you might remember from way back when in August, project 1, you can go ahead and minimize that one. And then we just wrapped up project 2 in this long list of stuff. I'm going to minimize that one. Project 3, ta-da, achievement unlocked, level up. All right, so we're moving on to the last third project, urban cellular aggregations. Right? So you might recognize this banner image. It's the background image for my camera. And this was actually generated with an algorithm. I didn't really do much of anything. I just basically gave it an ingredient, a little small piece of geometry. And I wrote the algorithm, gave it the rules. I sprinkled on some of these ingredients, and then this was composed for me, right, by the computer using the algorithm, doing some procedural modeling. Right? So it's this idea that we're going to use these automated or generative systems to generate architecture for us. And then instead of making form, we will basically make the rules and let the algorithm generate formal options for us. Right. So I'll start here with a few quotes. One from Herbert Simon, who was was really interested in architecture, but also really interested in ideas about complex systems, and including organizations, and how things self-organize, how things emerge, and what complexity actually means. And so he was somebody in the 20th century that did a lot indirectly to influence architecture. He wasn't an architect. However, he was sort of carving out these new definitions of complexity and how we deal with complexity. And so here's a famous quote by Herbert Simon in a paper he wrote called The Architecture of Complexity. Quote, by a complex system, I mean one made up of a large number of parts that interact in non-simple ways. In such systems, the whole is more than just the sum of its parts, not in an ultimate sense, but in the important pragmatic sense that given the properties of the parts and how they interact, the laws of their interaction, it's not a trivial matter or not an easy way to infer what kind of system it's going to produce, right? The properties of the whole. And so if you look at this right here, right? This banner image that I have my mouse on, I did not in any way, shape, or form sculpt this overall form, right? What I did is I gave it ingredients, I gave it the sort of rules for how to begin to aggregate or accumulate these ingredients in particular ways, how they interact with each other, to kill some of them off and to create offspring in order to create more, right? And at a certain time in the sort of evolutionary clock of this generative algorithm, I stopped it and froze it, and this is what I had, right? And so it's not necessarily something that I can reduce back to a bunch of parts, but it's a bunch of parts and a bunch of non-simple interactions over time. The results, one of which you see here, right, emerge based off of a bunch of non-simple or complex interactions, right? And even starting with a very simple part, that's what we'll do. We'll be creating a very simple very simple geometric ingredient, but the sort of complexity of the interactions and the repetition with how these things get aggregated over time is what creates this sort of complexity. Now let's bring this back a little closer to architecture with a quote from Cristiano Ciccato, who is now one of the design partners for Zaha Hadid Architects. In a paper he wrote actually quite a long time ago now, 20 years ago, yikes, in 2001. He writes, quote, "A fundamental paradigm shift in which instead of crafting a single solution, the architect or designer can now create a system or an algorithm which can produce countless variant solutions from the rules and mechanisms that respond to particular phenomenons, conditions, or intentions." A lot of big words here, but if I sort of distilled this sentence maybe a little further, right? Sort of rethinking an entire paradigm for how we design architecture, right? One, shifting away from the architect crafting the actual architecture to one in which you're actually crafting the algorithm, right? And programming and scripting these things and letting the algorithm do some of this heavy lifting and sort of taking the rules and all of the sort of contextual influences, maybe climate data, maybe pedestrian quantities, etc., and starting to generate an architecture that responds to a particular set of rules in particular ways, right? And if that happened, it wouldn't necessarily be a bad thing. It's not like we're replacing ourselves, but it's this idea, this paradigm shift where computers become partners or interlocutors, right? The designer and the computer form a partnership of complements, each contributing specific abilities and knowledge in order to create architecture, right? This overall task of architecture. And so if you think about computers and softwares and algorithms as tools to be deployed by designers and architects, I think they're fundamentally different than the sort of tools that we use when we're talking about pencil and pen and paper, right? And so beginning to sort of think about an architecture of our time that is really highly influenced by the technology of the time, right? Computers can do, I think, different things than what we would do with pencils. But in this case, computers can begin to generate things that we might not even anticipate that might satisfy, the sort of fitness criteria that we set up in the beginning, right? So this idea that you're not necessarily shaping directly architecture, but that maybe indirectly you're shaping architecture by directly shaping the algorithms that can generate things. And then it's a game of orchestrating as a designer, what kinds of rules and influences go into sculpting the form of a building, right? Maybe it's responding to sun, wind, and light. Maybe it's responding to its urban context, right? Height, scale, form, setbacks, responding to the street, responding to car traffic. Maybe it has to do with the program on the inside, making things pop in and out, push and pull along the overall form and shape of things, etc. Right? Anyway, I've seen this. It's interesting that these systems have been around for a long time, and 20 years apparently. Time flies. But now, even interestingly, I saw an ad for Autodesk Revit. Right, they have these sort of generative tools now that they're incorporating into Revit. And they were showing some, I think, pretty interesting things, but also some pretty mundane things like how to arrange a sort of apartment building footprint onto a site to maximize the amount of units and maximize the number of parking spaces you would need. So really sort of mundane stuff that I was like, that's kind of makes me cringe a little bit, but this idea that if you can sort of embed the rules of design into an algorithm and give this algorithm some sort of fitness criteria that it can work towards to sort of make better, more efficient, or working towards something that's genetically fit, right? Then you can begin to really, I think, deploy these tools in a really interesting way. And I think it's starting to happen more and more. Our industry is very slow to change and evolve compared to other industries. And yet, it's finally starting to take hold that these tools can fundamentally change the way we design things in our relationship with our design tools as a result. All right, so enough of me talking. We'll talk just quickly here, an introduction titled Urban Cellular Aggregations. This project will explore and deploy generative systems. Specifically, in this case, the type of generative system we're going to be using is called a cellular automata, right? So a CA for short, in order to aggregate small units into larger systems that populate and form a larger urban fabric. The objectives of this project are to understand how generative systems can be leveraged in the design process to create something complex, to generate massing design scenarios using the CA system, and then to draw, generate, format, and craft a set of projective drawings. We'll be primarily using axons. We'll do one perspective by hybriding rendered raster graphics and hidden line vector drawings from the things that we generate or that are generated by our algorithms. In this case, we'll be using Rhino and Grasshopper, Adobe Photoshop and Illustrator. In addition to Grasshopper, we'll be using a plugin for Grasshopper called Rabbit, developed by Morphocode. A little bit about that in a minute. The final deliverables will be 3 drawings of standard size and format, each demonstrating a unique urban cellular aggregation prototype. These will be submitted digitally in PDF format. The goal, as always, is to create the best, richest, and most detailed drawings you've ever created. You'll find that Rhino is going to do, or actually Rabbit and Grasshopper and Rhino and Illustrator will do the heavy lifting, a lot of the heavy lifting for us in that sense, because we'll be doing this work in class together, right? Terms and definitions. So what do I mean by aggregate, right? In the title of the project, it's called Urban Cellular Aggregations. So this word aggregations, when we talk about aggregating something, right? An aggregate as a noun is a whole formed by combining several elements together. Formed or calculated by the combination of many separate units or items, right? So it's this whole produced by a bunch of little small items, small units. The verb to aggregate something is to form or group into a class or a cluster. I like that word cluster, right? Aggregation then is the formation or clustering of a number of things, right? The formation of a number of things into a cluster, according to Oxford Dictionary. All right. So we'll talk about specific things to the cellular automata and Conway's game of life here in just a moment. But let's talk about some common generative systems and how they're used out in the real world. The first one we'll start with is called an L system or a Lindemeyer system. Okay. A Lindemeyer system starts with something very simple, right? And mathematically, it starts with some sort of axiom and then a set of rules, right? So for instance, this axiom will be starting with X, and then for every, F and X, and then every iteration or every generation afterwards, it'll replace every X with X plus a Y, an F, and a plus, right? And then there's a second rule, take every Y and replace it with F, X, Y, right? So there's a sort of nomenclature here for how to write these systems, right? But they're recursive. And they basically start to grow through a set of ticks or iterations or generations, as you'd like to call them. So if I just set my generation to 1 and I press start, okay, I get nothing. I'll take generations to 2 and start. I get something very simple, right? I get a line and the branch then turns into a line and a line, right? So things are turning at right angles based off of these rules. Try 3 generations. Okay, 4, 5, right? And this is all just drawing a line and it rotating by 90 degrees according to these rules, right? So at a certain point, these start to exhibit recursive behavior. In other words, they start to become fractal, right? You start to get the more you zoom in, the more you start to understand, you get smaller self-similar objects composing the larger self-similar shape. And so you can begin to see these sort of self-similar shapes sort of manifesting at different scales, which is a fascinating phenomenon called fractalization. So I'll start to up this is 6 iterations. I'll now go to 10. I'll now go to 30. You can tell, or you can see by 30, it takes a little longer to generate. And a string too large. Oh gosh, okay. Maybe 30 was too large for this little web app that's running in my browser. I'll set it to 20. It's still rendering it out. Now, here we go. Now, if you look at this, see if I can zoom in. I thought maybe I could, right? I'll go down to 15. Maybe that'll give me something a little more responsive, right? You can see that if I zoom in, it's actually quite dense. Oh, I thought maybe I could zoom in on the actual canvas here. Anyway, you can begin to play around with these rules. If I set the angle to 45 degrees instead of 90, I get something much more different, or 30, or 120, right? Okay, I can begin to look and see what other kinds of things I can play, right? So this is 7 iterations, an angle of 60 degrees. You start off with an A, and then every generation you replace A with B, A, B, and then every next generation replace B with A plus B plus A, right? And so again, as you start to tick through the generations, you start to actually increase the amount of detail, right? And so you can begin to see, you can start to develop actually quite an interesting sort of set of patterning here, right? Just by generating or changing a few of these parameters, right? The angle, the number of generations, right? The axiom, and then the rules, right? One small change in the rules can lead to a dramatically different quality of the results, right? As an example, oftentimes, at least back when they started, the way to generate sort of trees and vegetation, right, was to think about Lindemeyer systems, L systems, right? Because you think about changing that angle, and then this sort of idea of taking a branch that then gets replaced with a smaller branch, and then each member of those branches get forked, and every member of each fork starts to get forked, further, right? You start to generate basically something that begins to mimic plant life and growth, right? So you can begin to sort of look at different patternings, right? And that's what L systems were primarily thought of, as these sort of branching systems. All right. Another example, if you think about birds in nature, and you've ever seen a swarm of birds, it's really kind of an interesting phenomenon. Sometimes I'm talking about more than just a V of Canadian geese, migrating around this time of the year to southern locations to get warm. But if you think about these birds, these phenomenon, it's really quite an interesting thing, and it's something that's been simulated. This is, again, I forget the person that came up with this, but this is a very famous simulation of this phenomenon for swarm behavior called Boyd's, right? So if you think about saying birds, but with a New Jersey accent, like you were part of the cast of Grease or something, and said Boyd's, BOIDS is actually an acronym for, actually, let me look that up, by Craig Reynolds, 1986, right? I guess it was just short for birdoid object, right? But these sort of idea that each of these triangles in this case is an agent or a bird, right? And where it goes in its path is actually partly governed by its own, but also partly governed by all of the birds next to it, right? So if you think about the sort of system, the Boyd's, right? It's sort of an artificial life program, right? And so it's another example of emergent behavior where you get these crazy phenomenons, these sort of larger compositions and patterns, right? Based off of all of these, or generated by all these individual agents, right? Adhering to a simple set of rules that govern how they interact with each other, right? The rules applied to the simplest Boyd's are as followed: separation, right? So as you're flying, you're sort of trying to keep the same path, but you're also trying to keep a certain amount of separation from any sort of the closer birds next to you, right? So steer to avoid crowding from any of your flock mates that are close to you. Alignment, steer towards the average of all of the local flock mates, right? And then cohesion, steer to move towards the average position for the center of mass for all of the flock mates. So you can begin to tweak those rules, but in a way, they're always trying to follow the swarm. But on the other hand, they're also trying to sort of avoid smashing or crashing into any of the other agents, right, or any of the other Boyd's around. And so you get this behavior where, you know, these things, the larger sort of behavior drives all the individual agents, but at the same time, because they're trying to align and separate from each other, they're also starting to, in an ordered way, start to inform that sort of a larger emergent behavior, right? So it's a really sort of fascinating way to begin to these sort of dynamic systems, right? And this is, again, what we mean by complexity, right? These shapes and patterns, right? These complex phenomenons, right? We know that they're made up with a bunch of birds, or boids in this case, right? But it's not so easy to sort of figure out, given that we have, let's say, 30 boids, and here are the rules, what they'll actually generate at the end, right? It's not something trivial. We actually have to let it play out through the algorithm in order to sort of understand things. And we couldn't just look at the overall form and then deduce the rules, all of the rules and interactions, right? So we can't just reduce it to a bunch of, you know, like, it's not like looking at a brick wall where we can just reduce it to a set of bricks, right? And we understand the rules quite logically as, you know, sort of a common bond. You know, we lay down a row, then we stagger and lay down the next row, we stagger and lay down the next row, right? In this case, it's much more complex than that, right? All right. And so you can begin to see that there is coherence, separation, alignment in the visual range, so that, you know, how far they can see in order to sort of, you know, start to adhere to the sort of overall average direction, right? So if I turn coherence down, you can start to see that they start to scatter more. If I start to turn the separation up, right, you can see that there's fewer, you can start to see a lot more like sort of local movements, because you know, we're starting to amp up the idea that they can't collide, right? With alignment, we can turn the alignment up and turn the coherence up, turn separation down, right? And what you'll see is that over time, as each of these swarms start to get closer to each other, they begin to inform each other, and eventually they'll grow back into one full swarm again, right? So by simply changing those parameters around, we can take a large swarm and branch them off into smaller swarm behaviors, or we can get them, you can start to see that they're starting to adhere a little more, and we're starting to, you know, some of these smaller swarms are starting to get eaten up by the larger swarm. And over time, if we let this play out, I would suspect, right, we can start to get some more and more coherence here, right? All right. So again, I draw this out not because it's something that you're going to, you know, necessarily use in let's say your third year studio projects or anything, but there are, you know, serious folks actually doing some pretty interesting investigations with how these can begin to inform architecture. And sometimes what's interesting here is I can have it trace the paths over time. And what would be really great is if I could say the length of the time that the path is traced, we could begin to start to draw our own lattices with these sort of swarming agents, right? That could be kind of an interesting thing. But there are folks that look at this stuff and do interesting things here. You know, I look at, you know, looking at agent-based continuum structures. This is all about, again, you know, this is a paper from a researcher buddy that I know. Let me just see if I can move this out of the way and zoom in here. But what you can see is that if you start to look at these agents and their paths, right, you can begin to generate organization, form, structure, lattice, etc. Right? So looking at, in this case, a diagram of the paths, and then the paths, and then sort of tracing instances of those paths over time, you can begin to sort of generate maybe perhaps an architecture of complexity here, right? In this case, they were using Grasshopper, and looks like they were trying to optimize something with Galapagos, which is an evolutionary solver in Grasshopper. Right? So as you can see, you can begin here, they were looking at how these things might actually begin to subtract from a larger wall in this case, right? And you can see, you know, looking at, instead of maybe the negative space, looking at structure, sort of thinking about how that might work. Folks looking at, let's see here, you know, how they can begin to generate dynamic form. Let's see here. Here's one taking a larger shape or larger volume and figuring out how to create a sort of network of structural members using swarm behavior, right? So, and what's interesting is the swarm behavior becomes informed by a finite element analysis. So looking at the, let's say the structural stresses of shear, moment, and some of those other, let's see, shear, moments, and bending, right? Some of those things that you're probably thinking about or talking about in structures core class, right? So here's a cantilever, sort of looking at those stresses, letting those stresses inform some sort of generative algorithm to generate, again, to generate the structure underneath. And what I see, I don't see this a lot in architecture yet. Where I do see it a lot is in the engineering of all kinds of things that would either be cast or 3D printed out of metal, rubber, plastics, etc. Right? So I see this a lot in product design, and I see this a lot in high performance components for planes and other sorts of vehicles, cars, etc. Right? Where you're looking at a lot of dynamic stresses, you're looking at aerodynamics, and you're looking at heat dissipation, right? So we're looking at let's say the amount of surface area you have for energy transfer, right? So it's a kind of an interesting way of thinking about architecture, in that it's not the traditional way that we learn how to think about architecture, right? Anyway, but it's all dealing with performance. So what we're going to be dealing with is a cellular automata, right? It's a growth algorithm or sort of an algorithm that deals with a grid and populating the grid with live cells, and then letting those cells populate, reproduce, or die based off of a certain set of rules. The most famous cellular automata is called Conway's game of life, right? Way back when I first got my first laptop and was running Windows 3.1 or something, right? It came with some games. One of them was Minesweeper, and another one was called Game of Life, right? So I don't know if any of you have experienced Conway's Game of Life, but if you think about a grid, and each cell in the grid is white until you click on one and turn it to live. You create a live cell. Maybe it's set to black, right? What happens then is you wind the clock up and then you let it go, right? And based on the configuration of the live cells and these rules, right, they begin to reproduce or die, right? So if you think about this, a two-dimensional orthogonal grid of square cells, two possible states, live or dead, right? So you start off with the pattern that you want populated. Every cell interacts with its eight neighbors, horizontal, vertical, and diagonally adjacent, right? The following transitions occur at each generation or each tick in the clock. Any live cell with fewer than two live neighbors dies, as if by underpopulation. So if you just have one cell out by itself and no neighbors, it's going to die in the next generation because it's underpopulated, right? If you have a cell with 2 or 3 live neighbors, it lives on to the next generation. Perfect. So it'll stay in a sort of stasis state, right? It'll continue. Any live cell with more than 3 live neighbors dies due to overpopulation. And then any dead cell with exactly 3 live neighbors in the next generation will become alive as if by reproduction, right? So any live cell with 2 or 3 live neighbors survives. Any dead cell with 3 live neighbors becomes a live cell. All other live cells die in the next generation. Similarly, all dead cells stay dead, right? And so if you think about a simple set like this, if you start with 4 blocks like this, they stay in a state of homeostasis, right? They don't change at all. Same with the beehive, right? Because each of these have 2 or 3 live neighbors. They don't change. There's not enough neighbors to reproduce or create new neighbors, right? With this configuration, it'll just keep going back and forth. Again, in a state that's predictable, yet constantly toggling back and forth, right? Same with Toad and Beacon. Some of these others like gliders and spaceships and other sorts of things that nerds have labeled apparently and agreed to, then start to continue to reproduce, but they move or migrate across the screen in this sort of repetitive way, right? You can start to see these things manifest. This isn't hard. If you look up Conway's Game of Life, you can find a lot of simulators here. So in this case, the gray are dead cells or the sort of substrate that we can grow cells on. Here we have live cells, the yellow. And this looks like a glider. So if I hit start, see each simulation or each tick over here is a generation, 17, 18, 19, 20. This thing will move across. Now, if I start to add more live cells in different places, right? I'll just do this really quickly. Okay, and I'll hit start. What you can see is that these things start to interact with each other over time. Some of them achieve, like this one, we'll just keep toggling back and forth until this actually gets close enough and interferes with it. Or maybe it doesn't get close enough. Oh, there it goes, right? Now we have a set like this. It'll be really interesting to see if this grows and gets. So anyway, if you think about this, I'm going to stop it for a moment. You can just keep going to the next generation one at a time. If we thought about this generation, let's say 111, and we plotted those out as, let's say, cubes in an urban environment. And then for the next generation, 112, I'll hit next. We stack those as if they're in the next floor of units on top of the previous units. And then the next set for the next units, the next set for the next units, we can begin to create a sort of vertical urban aggregation. In this case, maybe they're square or L-shaped condo units or something like that, right? And so that's essentially how we're going to use Conway's Game of Life and the cellular automata in order to generate urban fabric, all right? Okay, and so using, again, the cellular automata, it's a collection of colored cells, turn on or off or live or dead, right? Based off of the rules and the number of steps you perform, you start to get these sort of patterns, right? Conway's Game of Life is a familiar example. We just talked about that. And in fact, there's a, if you want to learn about that more, again, just go to, again, our project 3 introduction page here. That's what I'm on, okay? The outcomes will look like this, right? So what you'll do is you'll take, let me just see if I can zoom in on these a little. No, I guess not. Oh, come on, right? Maybe I'll just zoom on these a little larger, right? You'll design a little ingredient, and then you'll populate a cellular automata, right? The initial starting condition in an urban environment with some existing buildings and some roads and blocks, and then you'll basically let the clock go and generate floor by floor sort of urban aggregation, right? That's much different than, let's say, 20th century way of thinking about our cities, right? So in some cases, we could generate new things. In other cases, they almost look like they graphed onto the sides of existing structures, right? And you can see folks using different ingredients here to generate different things. Different starting conditions generate different results as well, right? And so by simple algorithm in a bunch of simple ingredients, we'll each generate different complex sort of blocks of urban city, right? If we have time, we'll see, then we'll do a perspective as well, but we'll see about that, right? Here's kind of what the final results will look like, right? You'll do 2 of these, right? And we'll do these in class, right? But you'll be given a sort of urban environment that I'll show you in a moment. And then you'll be given a Grasshopper definition that you can run with Rabbit. And then you basically start to, tick the slider or let the timer go and watch this thing sort of build up vertically. You can then, we'll generate the sort of axons and renderings, line drawings, make 2Ds and things like that. Hopefully we get to some sort of perspective that we can just make a sort of atmospheric urban perspective of some sort, right? We'll see, well, if we get there or not. But I'm a man of my word. If we don't have time for it, that's the first thing that's going to be cut. I want these axons, these sort of on 11 by 11 Illustrator documents, right? All right, and so really quickly, I'm just going to show you guys. We're not going to start today. But I did want to sort of show you, this is kind of how it's going to go, right? I'll give you a sample of urban fabric here, not this whole thing, but you'll start to on the Monday when we meet, you'll have some quick rules that we'll do together, so that each of you can generate a sort of unique unit, right, or ingredient, and then we'll start to populate things, and then the next day we'll start to look at Axon and make 2Ds, and then hopefully we'll have time for a perspective or two, right? What this looks like, let me just back up a moment. Oh, come on, really? There we go, cancel. Right. Let me just show you, right? As you go, you can start to bake out your results as you want. And then, again, the idea here is that this algorithm, all you have to do is change one small thing, and then you can start to get lots of different variations, right? So again, here I'm just using one very simple ingredient. It's like a cube, and then I offset the exact same cube as a copy, and I subtracted the offset cube away from the larger cube, right? So I end up with a shape that looks like this. Yeah, so really simple, really simple ingredient, right? But then, even running the same rules, changing a few of the parameters in the Grasshopper script, I can begin to add rotation. I can begin to jumble things together with some randomness, right? Some jittering. Or I can straighten things out and not use rotation, but then again, sort of jitter things in elevation, sort of jumble it up, sort of create this sort of more interesting relief pattern, right? So again, there's room for you to experiment here as you begin to generate. Wind the clock up and let Rhino generate stuff for you, right? Okay. Let me just open up one more file here if I can. Sometime today, Rhino. All right, come on. Say open. No, don't save changes. Scheme 1, scheme 2, unit 1, maybe. I'll try this, right? Urban site model. Here we go. Try this. So here I am with a more complex unit, but you get the idea here. Let me turn this on to X-ray or ghosted. Let's try ghosted. I like ghosted a little better. There we go. So on Monday we'll open up Grasshopper just to sort of give you a preview of what's to come. Oh, come on. Trying to remember which one of these to use. I'll figure that out by tomorrow, of course. But essentially, right, the Grasshopper script will overlay a grid over your urban context, right? Your urban model. In which case, then you can start to place points inside of the grids that you want, the cells that you want to be live. Let's see here. So if I say set multiple points, and I start to place some points around in different areas, turn off my ortho, that's annoying. You can, of course, just make your own points in Rhino ahead of time if you'd like, but all right. Then what's interesting is that these that are too far apart die instantly. What you can see is that each of these points, right, in this case, we have it set to 45 generations. right? So each generation then gets stacked onto the generation previously. And these things start to grow. If we then take their unit and begin to populate each of these points with the unit, I'm not sure why. Lori, come on. Said 1 point, and I'll just snap to this. All right, here we go. Now we're going to get a lot more of these, but up arranged here, right? Right. So now we start to get a stacked tower of these units deployed along these points. All right, and so that's what we're going to be doing this upcoming week. The Monday and Wednesday before Thanksgiving, we'll be generating these things, doing some make 2Ds of the axons, and then in class the following week, we'll be putting them all together to make these 2 or 3 drawings that are the sort of final outputs. All right, cool. So I'll just, let's see, go back to Canvas here. All right, let's talk about that. So you can see some of these results here of the sort of outcomes that you'd expect to get, right? And hopefully that's helpful to you, as well as this PDF that I opened up. That's a link there too, right? These are examples from years past, and I can show you more. Today was the project launch. Again, I know you guys are busy. Trust me, I've been there. No one's not busy at this time of the year. So I know. All you have to do is come to class. Come to class on time. You'll get this project done without having to spend any time outside of class, except maybe to upload your PDFs, right? On Monday, when next time we meet, we'll have a synchronous workshop where we work on these step by step. I'll have some files for you to download. You can download it ahead of time or download it at the beginning of class. They'll be up on Canvas ahead of time. We'll be able to do these things step by step together. Wednesday, again, the day before Thanksgiving, synchronous workshop. You know, again, since we're remote, even if you're traveling that Wednesday, you can still log into Zoom and do it. You know, I don't know if you're going home to Oregon or Hawaii or California or New York for Christmas, whatever. It's not Christmas, Thanksgiving. Even if you're at home or not on campus, you can do it. Then Monday and Wednesday when we get back, you know, again, so we have basically 4 more class meetings, right? And if you come to each one, you'll get this project done in class. Very simple, very, very simple, all right? In case you do need more time, and some people do things the hard way, I don't understand why, right? These won't actually be due, the final versions, until basically the end of finals week, right? So Friday the 10th or something like that, right? But I would encourage you to just come to class on time, do this, get it done, right? And turn it in and not have to worry about it, right? You can basically just do it in class and not have to worry about anything outside of class for this, you know. While I know you guys are working really hard on your final studio projects and presentations and etc., right? So, all right. So that's my promise to you. If you go, again, I'm just going back to the modules here, go to the project 3 that's set up, right? Project 3. We were on the project 3, the sort of introduction page for the project. If you go to today's 17th of November introduction installation, right? Okay. You can see here, this is an example of, you know, some of the models that, let's say, at the Bartlett School, one of the most famous and best architecture schools in the known universe, right? Look at this. They do these things too. And so we're doing this as a fun exercise over 2 weeks, you know, as undergrads, just sort of learning about something new and keeping an open mind and doing something light in class. But there are serious folks looking at these sort of systems and rethinking our cities, right? If you can think about this for just a moment, right? I mean, I don't know about you. I mean, I've worked at plenty of architecture firms over the years. We didn't have a lot of time and overhead, you know, money just to throw at doing R&D and research and development with these sorts of things. Academia, the universities, we're perfect for doing these sorts of things, and that might be useful, you know, down the road, right? And so, you know, what's interesting is that, you know, sort of performing this sort of R&D, rethinking our cities, right? Looking at technology and how they might be leveraged to sort of change things for the better, right? And maybe they get absorbed by industry, you know, down the road, right? So think of us as sort of carving that out and doing our part and sort of picking up the sort of research and development ball and just inching it a little further, right? But anyway, you can begin to sort of think about if this is how buildings would grow, then maybe our cities would be dramatically different, right? In the future. All right, your only outside assignment for this class for the rest of the semester is to visit this link to Morphocode's website and download and install the Rabbit plugin for Grasshopper. I believe it works for both the Windows and Mac version of Grasshopper. You log in to download. You just have to create a quick login. That's so they know who, like, you can just use your UNLV accounts and your they don't collect a lot of information about you or anything. I think they just want to sort of understand who's using this or where people are that are using this. So, you know, they look at this and they go, oh, 30 people from UNLV, Las Vegas, huh? Interesting. Anyway, but what that does is it also lets them understand how many people are using it and whether they should invest their time into continuing to update it and improve it. So log in and download. It's not only just to download it, but it'll give you instructions for how to install it, right? So if I go to log in and download, I'll just try this. I can't remember what I used here. I suspect your password is the same as mine, ... Let's see. Oh, crud. Of course. Let's see. I can't remember what oh, right here. Actually, let me just pull up what you'd end up downloading. There's probably instructions in there. Again, I just want to make sure that everybody's on the same page here, because it's not just simply clicking a .exe file. You got to, there's some procedures you have to do to install this, right? So just simply following those instructions will help you out immensely. Let's see, parakeet, wasp, rabbit, CA. All right, here we go. Nope, where'd it go? Morphocode rabbit, here we go. Get started with rabbit.url, right? So that's a website, course details, tutorials, intro, install. Right? So you can download it here, install. You got to go into Grasshopper, go to the file pool. I mean, like there's instructions here, right? If you follow these, should be fine, right? Start using Rabbit. Okay. So you got to go into Grasshopper, file, special folders, open up the components folder, drag and drop that GHA folder in, then close down Rhino, restart it, restart Grasshopper. You should see the Rabbit toolbar in the tabs. Right, there is something else. I will mention this. Don't worry, these are like from old, these are really old things. These work with Rhino 6 and Rhino 7, I think. So, because I can use them in Rhino 6 and 7. Let's see. I was just trying to see if they had anything about, sometimes in Rhino, or sorry, in Windows, you have to right click on something that you've downloaded and unlock it, because Windows doesn't want you to just, any file to be downloaded to your system and then potentially be ran without you knowing. Okay, so if you run into any problems like that, let me know. Okay, right, but again, there's the instructions. You get those instructions after you download it, right? That's part of the zip folder, right? That you download. All right. Okay, so that's your only assignment. Everything else is in class. If you show up to class, you don't have to worry about rewatching my recorded lectures. You don't have to worry about doing work outside of class, right? Just come to class. Just come to class. All right. Okay, I'm going to stop recording.